Solving exponential equations. So today we're going to determine the solution to exponential equations when bases are of common powers. Quite get into solving equations with bases that don't have common powers or common bases until we start to talk about logarithms. So before we begin today, we just need a quick refresher on all of our exponent laws. So product of powers, a to the power of m times a to the n, would equate to a to the n. We add the exponents. If we divide powers with common bases, we subtract the exponents. Power to a higher power, we multiply them. Power of a product, if we're multiplying two values that are both taken to the power of n, that power of m is applied to both bases. Same thing if we're dividing two bases all to the power of m, that exponent is applied to the power of 0, we know as 1. Our negative exponent law tells us that we want to change this positive by reciprocating the base of this value, so 1 over a to the power of m. And our rational exponent, a to the m over n, can be written as a radical, where the denominator becomes the base becomes our radicand, and then that's all taken to the higher power of the numerator. So before we get into solving today, we're just going to do a quick review on changing a base to a different base. So for example, given 9 to the power of 2x, if I wanted to change this to a base of 3, 9 can be rewritten as a base of 3 to the power of 2. 3 squared equates to 9. And then this is still to the higher power of 2x. So then a power to a higher power, we'd multiply those exponents. So this would simplify to a 3 to the... Similarly, 125, if I wanted to write that as a base of 5, the equivalent expression would be 5 cubed. And then that would be in brackets. This needs to go to a higher power of 2 minus x. So if we're given this binomial, power to a higher power, we need to expand that through both values of that binomial. So our simplified expression would be 5 to the power of 6 minus 3x. Question C, if we're multiplying two values and we want to change this to a base of 2, well, order of operations tells us I cannot multiply these bases together until I've applied my exponent value, because we need to do exponents before we multiply or divide. But our exponent is an unknown, so technically I can't multiply these values. So rather than multiplying these, I'm going to change both of these bases, which would be 2 cubed, and then this would become 2 to the 4 to the higher power of x, which would just be 2 to the 4x. Now that these are common bases, I can go up to this power of products, and when I multiply powers with common bases, I would add the exponents. So my simplified version would be 2 to the power of 3 plus a 4x. Okay, question D. If we want to change the base of 2. Right now, again, we want to find the equivalent form of 512. So 2 to the power of 9 is equivalent to 512. Power to a power, I'd multiply these exponents. Okay. But right now our power is not in the base of 2, it's in a base of like 1/2. So in order to write this as a base of 2, I would have to reciprocate this. And so when I reciprocate this, what happens is that a negative is going to be applied to my exponent value. All right, and then finally, 16 over 81 to the plus 2, we want to change this to a base of 2/3. So 2 relates to the 16 as 3 would relate to the 81. So if I wrote this as a base of 2/3, both of these would be taken to a power of 4. 2 to the 4 is 16, 3 to the 4 is 81, and then that is taken to a higher power of an x plus 5. So power to a higher power, we'd want to multiply these expressions. So my final expression would be 2/3 to the power of 4x plus 20. All right, so when we start to go and solve exponential equations, we want to be thinking about, we need common bases. So in order to solve exponential equations, it's very similar to solving rational equations, in the fact that if I were to solve this rational equation, what I want to look for is I want to look for a lowest common denominator. And so my lowest common denominator here would be a 6x. So to solve this, technically what you're doing is you're creating a common denominator in all of these fractions and then we're solving the equation. So I'd multiply both my values here by 6. So this would be over 6x. Here I'd multiply this value by a 3, which would become a 9 over 6x. And lastly over here I'd multiply this value by x over 6x. So we've learned in the past, in order to solve this equation, now that these denominators are equivalent, we can simply ignore these denominators and solve this equation in my numerator. So 12 minus 9 would give me 3 is equal to 2x, x 3/2. So we want to follow that same idea when we're solving an exponential equation, in the fact that once both sides of our equation are written as a single common base, we can then ignore our bases and solve the equation in the exponent. So what I mean by that, I'm going to refocus this, there we go. So solve each of the following of exponential equations. So this first example is really straightforward. Both are base, and they both are written as a common base of 4. So what I can do, similar to up here, once these denominators were the same, we ignore those denominators and solve the equation in the numerator. Same sort of thing here. We're going to ignore these bases and solve the equation that's in our exponents. So this would become, I'm going to completely ignore my bases and I'm going to solve the equation 1 is equal to 4. So if I solve this, I get a 5, x divided by 5 is 2.5, or 5 over 2. So let's just do a quick check on this, just to show you that by ignoring those bases, the solution is actually works out. So if I take 4 to the power of 2 times 2.5 minus 1, that should equate to 4 to the power of 4. Well, 2 times 2.5 is 5, would give me 4. So in fact, this is actually going to check out. Okay, solve all exponential equations. Our first step is to always create a single base on both sides of the equation, and then from there we want to create a common base on both sides of the equation, and then solve, and then ignore your bases and then solve the exponential equation. All right, so 8 to the power of 3x minus 2 equals 16 to the x plus 1. So I'm going to look at my two bases. They're definitely not the same in this case, so I'm going to change this. What would be a common base? It's to an 8 and a 16 would be a base of 2. So I'm going to rewrite 8 as 2 to the power of 3, and then that's to a higher power of 3x minus 2. And then 16 I'm going to write as a base of 2 to the power of 4 to the x plus 1. So now that my bases are the same, I can bases and solve the exponential equation in my exponent. So technically I have a 3 power to a higher power. So if I were to rewrite this, this would be a 9x minus 6 equals 2 to the 4x plus 4. So now I'm going to ignore my bases and I'm just going to solve the equation 9x minus 6 equals 4x plus 4. So this is a fairly simple linear equation. This is to one side, so I get a 5x over here. On the right side I get a 10. Divide by 2, x equals 2. So you don't have to check every question. I mean, you could check it on your calculator by substituting this into y1, putting this into y2 and find that point of intersection between the two, which would be at an x equals 2. Okay, so next, question number 3, right? We're given 6 to the 3x minus 1, 6 equals 1. So they're already written as a single base, but our bases are not the same. So I cannot change a 6 into a base of 1. That's impossible. But I can change the base of 1 into a base of 6, because we know any base to the power of 0 equals 1. So now these are written in the same base. I can now solve my exponential equation, move 6 to the other side, and we also get a value of x equals 2. All right, question number 4, right? So here we are given a 3 to the 2x plus minus 1 plus 1 equals 2. So in this case, we have two bases on one side of the equation, which we need to isolate this in order that we have just a single base on both sides of the equation. So I am going to move this plus 1 to the other side by subtracting 1. And so what we end up with is an equation similar to the last. We know anything to the power of 0 equates to 1, so I'm going to change this to a base of 3 to the power of 0. We have 2x minus 1 equals 0. Now we're going to solve. 2x is equal to 1. X is equal to 1/2. Those first 4 were pretty straightforward type of questions. They obviously get a little trickier, which is represented in like. All right, so I'm going to look at these two bases. This is a 27. This is a 1/9. Similar, a base that would be common to 27 and 9 would be a base of 3. So I'm going to change this to a base of 3 to the power of 3, all to a higher power of x plus 3. In order to change the 1/9 to a base of 3, I would need a negative exponent on my base of 3, and 2 would give me 9, so it'd be 3 to the negative 2. Now that these are, so a second step, power to a power, we multiply. Now that these are common bases, I can ignore my bases and solve my exponential equation. Move 4 over here, make my x's positive, subtract 9, my x is equal to a 1/7. Okay. Okay, the last one, definitely a little trickier. So what I want to do is, again, I want to create, it looks like a base of 3 here. So 9 would be 3 to the power of 2 to the higher power of 2x. In my denominator, 3 to the 3 to a higher power of 3x minus 1. On the right side, I'm given a radical here. So if I want to change this to a base of 3, the exponent is going to be a rational exponent. So the denominator of my rational exponent, and the exponent is the numerator. So it becomes 3 to the x over 3. Okay, so using those exponent laws. So again, this is still not written as a single base. So my next step is I'm going to power to a power, I'm going to multiply these values. Now, this is still not written as a single base. So now we have to use our exponent laws and think about, well, what do we do with exponents when we're dividing with common bases? We want to subtract our exponents. So I'm going to take a 4x and subtract a 9x, which would give me a, oh, and sorry, this is all still to the exponent of 3. So if I subtract these, I get a 3 to the negative 5x. And then technically this is 0 minus a negative 3. So that's going to become a plus 3. And then this is all still taken all to the power of 3. Okay. So now, power to a higher power, we want to multiply these exponents. So this becomes a 3 to the negative 15x plus 9 equals 3 to the x. All right, so now that these are finally in a common base, I can solve this exponential equation. So I'm going to cross multiply my 3, becomes a negative 45x plus 27 equals x. I'm going to bring to this side, which would become 46x, divide by 46. And my final answer for x would be 27 over 46. Okay, definitely standard of excellence question, kind of tricky. Okay, so after solving equations, the last thing we're going to talk about is we're going to introduce another formula for solving like exponential functions. Okay, so we're talking about doubling time, half-life time formula. Okay, so similar to our basic exponential equation formula that we use for compound interest, it's a times b to the power of x. This formula actually relates to doubling time or half time. So in the question, it'll tell you how long it takes for something to double or be cut in half. And so when we see that wording, we want to relate to this formula. All right, so our A value still represents the same as our compound interest. Our A value is going to represent the initial amount of whatever we're talking about. B represents the constant that's happening. So if in the question it says doubling, then B would be 2. If it talks about half-life, then we're cutting things in half over time, and our B value would be 1/2. If it says tripling, right, quadrupling, then that value would be a 3 or a 4. So time represents the total amount of time that's elapsed in the question, and represents the period of time that it takes for something to double, triple, half, or whatever the question's talking about. So for example, it says a radioactive isotope has a half-life of 7 years. So what it means, it takes 7 years for the mass of this radioactive isotope to be cut in half. So if initially there was 400 grams of radioactive isotope present, it would take 7 years for that 400 grams to break down to 200 grams. And then it would take another 7 years for it to break down to 100 grams, and so on. The question asks, how much isotope is present after 20 years? So it's giving us a time that doesn't fall within our half. So it's obviously going to be not an even number, exactly like half of the previous amount. So this formula. So my A value is my initial amount, which is 400 grams. My B value, in this case, we're talking half-life, so B is going to be 1/2. The time elapsed in this case would be 20 years, and my doubling time, or sorry, half-life time, it takes 7 years. Half. So now we're just going to substitute these values into my formula. 400 times 1/2 to the power of 20 divided by 7. So on your calculators, we're going to, oops, forgot the 400. So to the power of, now you'd want to put the 8 divided by 7 in brackets or leave it in your exponent expression depending on what kind of calculator you have. And the answer would be 55.2 grams. So how much is left after 20 years? 55.2 grams. Okay, question 5. A bacteria culture of 50 cells doubles every 3 days. How many cells will there be after 2 weeks? Okay, so again, our initial amount of cells of bacteria we're starting with is 50 cells. Our B value, our constant in this case, we're talking about things being doubled, would be a 2. The time elapsed in this case is 2 weeks, but my doubling time is in days. Either have to change the days into weeks or the weeks into days. So we're going to change the weeks in this case into days. So 2 weeks in days would be 14 days. And then our P value, how long does it take to double? It takes 3 days. So how many cells would be present? Would be Y equals 50 as our initial amount. We're doubling this for over 14 days, and our doubling time is 3. So substitute that into our calculator, and we get a value of 1,270 cells are going to be present. Okay. All right, question B. How long would it take cells to reach 3,200? So in this case, we're kind of working backwards. In this case, we're actually looking for our time, how much time has elapsed for it, excuse me, for it to equate to time, or for it to equate to 3,200 cells. So this is the total number of cells, which is our Y value. Our A value is still 50. Our doubling constant is 2, and this is going to be to the power of T over 3. So our first step to solve this question would be to divide both sides by 50, which gives me 64. So what we end up with is an exponential equation that we need to solve, and so to solve this algebraically, we need to change this to a common base of 2. So 2 to the power of 6 is going to equal 2 to the power of 2/3, T over 3, sorry. Now that our bases are the same, we're going to ignore those bases and solve this exponential equation. So we get 6 equals T over 3, cross multiply days. All right, and then question number 6. It says the value of sports cars depreciate by 25% every 2 years. Write an exponential function to represent the above information. So in order to write our exponential function, right, our A value, right, we're not getting initial amount, but really we're talking about percentages here. So before off the lot, the car is worth 100% of its value. So as a decimal, 100% would represent just the value of 1. Our B value, it depreciates by 25%. So when we talk about a depreciation, we actually want to take this, subtract it from 1, because we don't want to multiply the car's worth by what it depreciates by. We want to multiply the car's worth by what it's still worth every 2 years. And every 2 years, if it depreciates 25%, then it's actually still worth 75% of its original value. So when it depreciates, we own minus the depreciation value. Okay, so in this case, 1 minus 0.75, or sorry, 0.25 would equate to 0.75. Okay, now we're just writing an exponential function, so that means we don't know our value of time. Time is always changing, but our depreciation time is every 2 years, so P is going to be equal to 2. So our exponential function would look like the following: 1 times 0.75 to the power of T over 2. How many years would it take to depreciate to 20% of its original value? So 20% of its original value as a decimal would be 0.2. So I'm going to substitute 0.2 in for my Y value. And technically I don't need this one in front because that's not going to affect. All right, so at this point, to solve this algebraically, we'd want to try and find a common base between these two values, which is impossible. We can't find it. And we have to put logarithms at this point. So the only way we can solve this equation at this point is to solve it graphically. So on your calculators, in your y equals, we're going to type our left side in y1, our right side in y2. We're going to kind of change our window setting a little bit. X, remember, represents our time, so I might want to go to maybe 10 years. -2, our y value, this is originally just 1. That's what we're starting at, and then it's changing. So I'm going to put that to a 1. So here's our exponential function. I'm going to change my windows again to just emphasize above my x-axis. So let's maybe put that to like 0.2. There we go. Okay, so what we're looking for is we're looking for this point of intersection, which we still can't quite find. So I'm going to go back to my windows again, change this maybe to 20 years, and then get a nice graph. All right, there we go. We are looking for this point of intersection, second trace, number 5 for intersect, enter, 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 and we end up with 11.2 years. Let's round to the nearest 10th. So how long will it take to depreciate? 11.2 years to 20% of its original value. Okay, all right, so that exponential equations.